Okay, guys, continuing lesson 5, we're now going to decide how to interpret standard deviation. How do we explain what it means? Let's say we computed it, but what does this mean? Okay, so let's think about the way we computed it. We took all of our observations, we found the average, then we subtracted the average from each observation, and we found something called deviation from the mean. Then we had to square them, add them up, divide by how many we have, then take the square root. It's a lot of computations, but everything depended on deviations from the mean, because we were subtracting the mean from each observation. And so standard deviation is interpreted as the typical deviation of the data from the mean. So when we compare two different populations or samples, if you have larger standard deviation, that means more spread in the data. And the spread is from the mean. So for example, if we know that the travel time data has a sample standard deviation of 20 minutes, how do we interpret that? Well, we'll say that typically the deviation of the data of the travel times from the mean is about 20 minutes. So on average, the data differs from the mean by about 20 minutes. Okay, so that's what standard deviation represents. Now, computing it and comparing it, let's look at the two data sets that we have computed or looked at in the beginning of this lesson. So let me copy them again into Desmos and let's compute the standard deviations and let's compare just to make sure that I got them here as correct. And it doesn't matter whether this is sample or population, but let's just assume this is sample. So then we're using stdv, right, without the p because that's a sample. And so if you round it, you get 1.49 for data set number 1 and 4.99 for data set number 2. So clearly the second data set had more spread. And remember, the second data set really did look like it was much more spread out than the first one from the mean. Okay, so that makes sense. And if you think about stuff like investments, for example, standard deviation is used to measure risk. So if you look at two different investments and one of them has larger standard deviation, that means this investment is riskier because the spread is larger. You really do not know what happens to this investment because today's goes down, tomorrow it goes up, it's all over the place, it's large spread is not good, that's risky, right? And so the larger the standard deviation, the more risk in the investment. Okay, now for this example, so we're going back to, let me just refresh the page, we're going back to the travel times. So let's just say L equals, and let's get the travel times again. So this would be these. Okay, and then we want to compute the standard deviation of this data. So let's decide what it is. Okay, I'm going to go ahead and surround it by the command round and 2. Okay, so the standard deviation is 9.08. Now, remember that range was not a resistance statistic, because remember, if you change one of the observations on the ends, like one of the observations, change it from 38 to 88, range will change. So range is not a resistance statistic, but maybe standard deviation is resistant. Well, let's take a look. Now I'm going to go ahead and just copy this over here, and I will call this some other name because Desmos doesn't like it. So just L2. By the way, all I'm doing is just typing 2. I don't need to do anything. It just automatically changes it to a subscript. Okay, and then what I want is change this last number. You need to see that first from 38 to 68, for example, and see if that's going to affect the standard deviation. So let me copy this here. Let's call this L2. And look what was happening. The standard deviation actually changed. Oops, this is the wrong window. This should be, oh, 1 second. There you go. Okay, so the standard deviation was 9.08 and now we changed to 17.82. So there is a huge change, and all we did was change just one number. So in conclusion, can we say that standard deviation is resistant? Because remember, resistant means it does not change. Well, nope, it changed. Now, why is it not resistant? The reason why it's not resistant is because when we compute standard deviation, we are subtracting each data value and then minus the mean, but the mean was not resistant either. So the mean changed, and of course the standard deviation will change also. Okay, so standard deviation is not resistant. Okay, so summarizing these two lessons 4 and 5, what you need to know is that the mean and median, range, and standard deviation, how do you compute them in Desmos? So this lists all the commands. How do we interpret them? Because that's going to be usually a multiple choice kind of question. For the mean, this is average observation of the data. For the median, it divides the data in half. 50% is below the median and 50% is above the median. For the range, this is the difference between the largest and smallest observation. And finally, for standard deviation, that is the average deviation or spread of the data from the mean. Now, in terms of resistance, we found only one measure that was resistant to outliers, one measure of center, which was the median, and that was resistant. But the other measure of center, which was the mean, was not resistant, and neither did the range and standard deviations, which were a measure of spread. None of them were resistant. In the next lesson, we are going to actually look at a measure that will be resistant, which will be called interquartile range. And that's the one that we will be using when your data set has outliers.